Basic examples in solving logarithmic equations. Property of logarithmic equations. If b is greater than 1, the logarithmic function y equals logarithm of x to the base b is increasing for all x. If 0 is less than b less than 1, then the logarithmic function y equals logarithm of x to the base b is decreasing for all x. This means that logarithm of u to the base b equals logarithm of v to the base b if and only if u equals v. There are 3 points that you need to remember in this property. First, when the base is greater than 1, for all values of x, the function is increasing. When the base is in between 0 and 1, for all values of x, the logarithmic function is decreasing. And for the one-to-one property, if logarithmic expressions have the same base, then we can automatically equate the two values. There are strategies for solving logarithmic equations. First, we can rewrite to exponential form. Take note that the logarithmic form c equals logarithm of a to the base b means a equals b to the power of c. Second, using logarithmic properties, you already know about the logarithm of a product, logarithm of a quotient, and logarithm of a power. Third, applying the one-to-one property of logarithmic functions, that is, logarithm of u to the base b equals logarithm of v to the base b if and only if u equals v. And then the zero factor property, that is, if ab equals 0, then a equals 0 or b equals 0. Let's have some illustrative examples. Solve for each logarithmic equation. Number 1. Logarithm of quantity 3x to the base 3 equals logarithm of 15 to the base 3. To solve this one, take note that the two expressions have the same bases. So, in that case, we can apply the one-to-one property. We cancel logarithm to the base 3 and then just equate directly 3x equals 15. Next, we need to isolate x. So to isolate that one, we need to divide both sides by positive 3. X is equal to 5. Now, if we try to check it, 5 is a solution since logarithm of quantity 3 times 5 to the base 3 equals logarithm of 15 to the base 3 is defined. Why is it defined? It's because the base is positive and the logarithm of that number is also positive. Therefore, x equals 5 is a solution. Example number 2. Logarithm of quantity 2x plus 1 to the base 5 equals 2. To solve this one, we need to change this expression into exponential form. So our base is 5 and the logarithm is 2. Therefore, if we change it to exponential form, that is 2x plus 1 equals 5 squared. Then simplifying, 5 squared is 25. So we need to isolate again x. Transpose 1 to the other side of the equation. 25 minus 1 is 24. Now isolating x, divide both sides by positive 2 and that gives us x equals 12. The question is it defined? If you try to check, 12 is a solution since logarithm of quantity 2 times 12 plus 1 to the base 5 is equal to logarithm of 25 to the base 5 is defined. Again, it is defined since the base is positive and the logarithm of the number is also positive. Therefore, 12 is a solution. Example number 3. Logarithm of 16 to the base x equals 2. We need to find the value of the base. To solve that one, we again change to exponential form. So it is written as x squared equals 16. Now transpose 16 to the other side of the equation since this already involves an exponent of 2. Factor x squared minus 16 equals 0 into quantity x minus 4 times quantity x plus 4. Apply the zero factor property. So we have two values of x's, x equals 4 and x equals negative 4. The question is, are these two values the real solution of this equation? To check that one, 4 is a solution since logarithm of 16 to the base 4 is defined. Negative 4 is not a solution since logarithm of 16 to the base of negative 4 is not defined. Remember, the base cannot be negative. X equals 4 is the only solution and x equals negative 4 is an extraneous solution. An extraneous solution, as I recall, is an apparent solution that does not solve its equation. Example number 4. Logarithm of quantity x plus 1 to the base 2 plus logarithm of quantity x minus 1 to the base 2 equals 3. Since this is addition, we can condense this expression by applying the logarithm of a product, so that would give us this line. Next, we change to exponential form. Our base is 2 and the logarithm is 3, therefore this is the exponent. So that gives us this line. Simplifying, we have 2 to the power of 3 is 8. And then quantity x plus 1 times quantity x minus 1, applying the special products, that is just equal to x squared minus 1, then copy 8. So we transpose 8 to the other side of the equation. That gives us x squared minus 1 minus 8. That's why we have here negative 9. Factoring x squared minus 9 gives us this quantity x minus 3 times quantity x plus 3. Applying the zero factor property, we have again two values of x's. We have x equals positive 3 and x equals negative 3. Now checking, 3 is a solution since logarithm of quantity 3 plus 1 to the base 2 and logarithm of quantity 3 minus 1 to the base 2 are defined. It's because the base is positive and the logarithm of that number is also positive. Negative 3 is not a solution since logarithm of quantity negative 3 plus 1 to the base 2 is equal to logarithm of negative 2 to the base 2 is not defined. It's not defined because this expression here is a negative. Take note, this must be positive for the logarithmic equation to be defined. Negative 3 is just an extraneous solution. So as a reminders, in the logarithmic form, logarithm of x to the base b, x cannot be negative.